In this video, we are going to define how to integrate a differential form along a curve gamma. And we will use that to derive conditions for a differential one form to be the total derivative of a function from the open set to the real numbers. First, let's interpret a one form as a vector field. Now, this interpretation is not canonical. What I mean by that is there is a choice involved. So this is not an ideal way of viewing differential one forms, but nevertheless it is useful. So what you do is the following. Suppose omega is a continuous one form on the open set U subset of Rn. Then I can write omega as sum a1 dx1 plus an dxn, where by definition a1 to an are continuous on U. So this is the definition of a continuous one form. Well, I do the stupidest thing possible, define a vector field f from U to Rn by x1 to xn, or rather let's just call it x. Let's not complicate the notation needlessly. It's just x going to a1x comma a2x comma anx. So I do the stupidest thing possible. I get n functions from the definition of a differential one form. I take all of these together and throw it inside an n tuple, and I call it a day and define the vector field f. The reason why this is not a canonical definition is for the reason that this representation of omega as a1 dx1 plus an dxn relied on choosing a basis for Rn to be the standard basis. Recall that dx1 to dxn are just new names given to the duals of the standard basis. Okay, so if I had chosen a different basis, not the standard basis, some other basis, then the end result would be a different expression. I would have gotten different a1 to an, and consequently if I do this identification I get a different vector field. Okay, so this is not a canonical identification, but nevertheless it's a useful identification. One can use this identification to define the definition of integrating a differential form along a curve gamma. Just look at the associated vector field and integrate that on the curve. A better way of doing things, a more intrinsic way that does not depend on any choice of basis, is to define what the action of a differential form on a vector field is. So if b1 x bnx is a vector field on omega, then by definition we can apply omega to this vector field. We can apply omega to this vector field. Recall that a differential one form eats a vector and spits out a number. This vector field for each point x in U produces for you an arrow, a vector. Omega can eat this vector and produce for you a number at each point. So we can define a function, omega of f from U to R, which is just x going to omega at the point x acting on f, which is a vector. Okay, so omega of x will give a linear functional. F of x is a vector. So omega of x can act on f of x, and this will be a number. This will be a number. And clearly if omega of x is a1x dx1 plus dot 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 a2 anx dxn, then clearly the action in our scenario, the action is x going to a1x b1x plus dot 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 anx bnx. A very natural action. Now it's utterly clear that if ai and bi are both continuous functions, then so is omega of f. If omega is ck smooth and f is also ck smooth, it's clear that this action omega of x acting on f of x will also give a ck smooth function. So now we can give an intrinsic definition of integrating a differential form along a curve. So integrating a differential form. Integrating one form along a curve. So the definition is as follows. Let U subset of Rn be open and omega a continuous one form. On U. Let gamma from AB to U be a C1 smooth curve. C1 smooth curve. We define integral of omega along the curve gamma to be just by definition integral a to b omega at the point gamma of t acting on the velocity vector gamma prime of t dt. Okay, the fact that this integrand omega of gamma t acting on gamma prime of t is actually a continuous function follows from the preceding discussion. So the integrand is in fact Riemann integrable, and this makes sense. Okay, now let us answer the questions that I asked towards the end of the last video. Given a differential one form on an open set U, how do you know whether it is actually the derivative of a function, differentiable function? If indeed omega is actually the differential of a function, how are you going to find this function? Okay, let's address these questions now with this additional tool of integration. What I am going to do is now give some standard definitions from physics. You might have also seen these definitions in maybe a course on differential equations. Let me just give these definitions. Definition. This is the definition of a conservative vector field and potential function. Conservative vector field and potential function. So the definitions are as follows. Let U subset of Rn be an open set. And let F from U to Rn be a vector field. Okay. We say F is conservative if the integral of f along any curve, any C1 smooth curve in U depends only on the endpoints of the curve. Okay, so a vector field is said to be a conservative vector field if you take two curves starting and ending at the same points of view. The integral of this vector field along both the curves will give rise to the same exact value. A function g from U to R is said to be a potential function for f is said to be a potential function for f if the gradient of g is nothing but f. Okay, so essentially when I say the gradient of g is f, the gradient vector field is exactly the vector field f. We can make a similar definition for forms, which is the notion of an exact form, and the definition here is as follows: continuous one form on U is said to be exact if it is the differential of a C1 smooth function that is zero form on U. This is sort of an analogous definition of potential function for differential forms, in which case it's called an exact form. So now we have all the things in place. We can state the fundamental theorem of line integrals. Fundamental theorem of calculus for line integrals. And the fundamental theorem of calculus for line integrals is as follows: let f from U to R be a C1 smooth function on U, and let gamma from AB to U, so be a C1 smooth curve. Then integral over gamma of the differential one form df is nothing but f of gamma of b minus f of gamma of a. So if you integrate the differential, you just get back the function evaluated at the end points with a negative sign in between. Okay, sort of very similar to the fundamental theorem of calculus. We can also phrase this for vector fields. For vector fields, we can say the integral over gamma of gradient of f is nothing but f of gamma of b minus f of gamma of a. Okay, so this is the fundamental theorem of calculus for line integrals. So to rephrase this, a vector field, so let me just add it as part of the statement of the theorem because it's nice to highlight this. A vector field has a potential function only if it is conservative. In other words, a necessary condition for a vector field to have a potential function is that it is conservative. We will later address whether this condition is actually sufficient. So let's move on to the proof of the fundamental theorem of calculus for line integrals. So write this this function f as f1 e1 plus dot fn en. That means I'm just writing down the coordinates of this function, and write down gamma as gamma 1 e1 plus dot gamma n en. That means I'm just writing down the coordinates of both f and gamma, and by definition both f and gamma are C1 smooth. Now what is the definition of integral of df over gamma? Well, if you just look at the definition, this is just integral a to b del f by del x1 at gamma of t into gamma 1 prime of t plus dot 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 del f by del xn at gamma of t, gamma n prime of t, whole thing dt. Okay, so this is just the very definition of the integral of the differential form df along the curve gamma. By the chain rule, the above expression is just integral a to b f composed with gamma prime of t dt. Okay, and now this f composed with gamma prime of f composed with gamma is just a single variable function. So this is going to be by the regular fundamental theorem of calculus in one variable, the classical one that you're familiar with for many years. This is just f of gamma of b minus f of gamma of a as claimed. Okay, now the proof of the vector field case is exactly the same. So the proof for the vector field version is exactly the same. Field version is the same, and I'm going to leave it to you. Okay, so what we have got is that if you have a vector field that has a potential function, then it is automatically going to be conservative. For the converse question, if a vector field is conservative, does it have a potential function? We will address this in the next video. This is a course on real analysis, and you have just watched the video on the fundamental theorem of calculus for line integrals.